Hi, this is the tutorial for TITAN-1-1M CAM programming. For you to proceed with this assignment, you must have completed the CAD portion of that same configuration of the TITAN-1-1M as shown on sheet 1 of the Titan drawing. So your first step is you'll go to the data panel if it's not already open, and you will open your TITAN-1-1M model, and by default it will be in model mode. We can close the data panel once you have the model open, and it should be just the block with the radiuses on the corners. The first step you have to take to do computer-aided manufacturing programming, so you have to switch from model mode to manufacture, which covers CAM. The menus across the top will change, and the history tree here on the left will be different. You do want to make sure that you are in inches. Our machines are all set up there in inches. The default was metric, and if this is displaying millimeters, you'll want to watch the first video for downloading Fusion 360, which goes over how to change those default parameters. We're going to move on to the next step. So the first thing you do is you're going to define a setup, and that's an individual setup on a machine, and it defines where the origin or location of the part is fixtured within the coordinate systems of the machine. So we are going to go to this pull down menu, and we're going to make a new setup. And it's going to default, it should default to setup number 1, and this menu will show up here. Now I modeled my part on model origin, so I'm actually going to flip the part to another orientation just so you can see how to change the axes on this orientation for the part. So we're going to assume this is the first side, and in this setup, the first thing you actually want to do is set up the information on tab 2, which is the stock size. So your model is the finished size of your part. The stock represents the size of the material you start with that you're machining down. So we're going to leave this at relative size box, and we're going to set stock offset mode. We're going to leave that to add stock to the sides, top and bottom. Our material is bar stock that is 1 inch by 2 inch by 4 inch. It's cut from a bar. The bar sides will be finished pretty well, and then the two ends of the 4 inch dimension will have saw cuts on them. So our model finished part is 1.9 wide, so we need to add 0.05 to the sides to account for the thickness difference between our finished part and our model part. And then on the top offset, we're going to leave about 0.4 to remove to skim cut the top of the material, and then the bottom is going to be 1 inch stock minus less this 0.04. I'm sorry, we have a 1/4 inch of extra material, so it's going to be 0.21. Our stock size should be 4.1 by 2 by 1 inch with the parameters set on this program. Now we're going to go back to the setup tab. Now Z is always in line with the axis of the machine, so that axis should be pointing towards the spindle. X would be our horizontal axis, and Y being our vertical axis on table movement. So the first thing we're going to do is we're going to set our orientation, and we're going to set it to the z-axis plane to be according to what we select in Z and the x-axis. So on that option, it changes the menus here below. So what I want to do on this z-axis is I want to select a plane that represents what would be perpendicular to the z-axis. So it's going to be this face. Okay, and as you see, the stock to add to bottom shifted to the bottom of the part. Now right now, the orientation of X and Y are backwards. So we are going to select now our X-axis, which is this edge, and we want to flip it. Okay, so now we have our X positive axis going in the same orientation as our screen is in relationship to the motion of the table of the machine. Now our origin, we want to set this as a corner because that's something that's easy to pick up. And we're going to base that off a stock box point. And what the stock box points are is they're points based off the stock. They're in convenient locations to register the part. So in this case, we're going to have it be the top left of our stock, which is right here. Okay, so now our origin has been moved. So we have our axes set in the correct orientation, and we have our origin on the left corner of our part, left corner of the stock of the part. Okay, so at this point, we are going to go to the last tab. And we're going to leave our program name for this because it's our first one as 1001. And our program comment is going to be operation 1. And that'll show up in the code so we can identify this program. And we want to use work offset world coordinate system or work coordinate system 1. That translates to G54 on the Haas machine, and that'll make some more sense when we start working in the lab. We're going to leave everything else at default and hit OK. So you've now created your first setup. Okay, now that we've created our first setup, which will be most likely with this block held in a vise with the x-axis being the fixed jaw on the vise and the bottom of the stock being held on this extra margin so that we can machine the top face and the sides, 4 sides of your stock. We will be doing a second setup that will machine off the extra material off the back to bring the part to thickness, which will require the material to be unclamped from the vise and reclamped, flipped over in orientation. So within this, we will do the first setup, and once we finish the programming, we will create a second setup. So our first operation is going to be called what's a facing operation. All it does is it takes down a large plane down to a certain height. And so we select 2D face, and this multi-tab menu box will show up. Now I've created programming notes. If you're having trouble seeing on your monitor the numbers that are being punched in, it's in PDF format. You can choose to print it if you like, and but it has box by box every tab that we'll be cycling through here. Okay, so if you want to follow along. Okay, so our first operation is going to be this facing, and we need to select a tool. So we're going to select a tool from the Titan building blocks library. Now, if you're not seeing this library in this window, you need to back up to the video tutorial that shows you how to download the tool library off of the Titan site. He has a standard set of tools, and it's what we use for the entire program. So stop the video here if you're not seeing the tool list, and go look in Canvas for the Titan tool library tutorial. Okay, so we're going to use tool 1, which is a what's called a face mill. The holder looks like this, and it has what's called a shell mill face that holds inserts on the corners. The display just shows it solid, but it's a very efficient tool for just removing a lot of material on a flat plane. Okay, here is shown an example of a shell mill, face mill, typical of what you're going to be using. We have a 3-inch Kennametal 4 flute or 4 insert shell mill, face mill. Now, face mill is the type of cut it makes, and shell is referring to that it's a non-cutting body that bolts onto a arbor, acting like a shell around the arbor, and that is the black component you see with the nut or the screw in the middle. And this particular example has 4 inserts, which are the light gray parts, and they are precision made carbide sharp inserts, and most of them are designed to be flipped or rotated for more than one cutting edge, and possibly flipped depending on the design, so you have more than one opportunity to use the insert before it's completely worn out. They're very accurate, and those inserts seat right in very accurately, so they can be changed in and out, and if your tolerances are appropriate, you don't have to reset the tool. The insert does have a radius on it, and so if you were to cut a feature that leaves a sidewall, you have to account for whatever the radius that's designed into that particular insert. We're going to select OK, and some information will change here. We're going to go very conservative on this. We want to give you plenty of reaction time for being new on the machines, so the performance of these tools can run at least double what the numbers I'm going to be giving you in production. But we want to make sure that we're safe and gives you enough reaction time to stop the machine if you have a problem. So we're going to go at 4,000 RPMs, which is how fast the spindle is going to be spinning. We're going to skip the surface speed box. It's auto-calculating, or if you know what the surface footage should be from the manufacturer, you can enter it there and it'll back calculate the RPM. The ramp spindle speed is going to be the same on this type of cutter. We're going to do a cutting rate of 30 inches a minute, 25 inches a minute, and lead in feed rate of 25 inches a minute. Our lead out the same. In this case, the ramp's going to be 25, and so is the plunge rate. Now, on a face mill, you don't really plunge the sideways moves or plunges, and you are always going to lead in and out off the material. So for that purpose, all these feed rates for this type of cutter in this application would be the same. Other types of cutters, plunge rate and ramp rate and lead in and lead out refer to how the motion, the speed at which the motion of the cutter will first engage the work. So when you first engage the work with a cutter that has to go straight down, may have 100% of its diameter engaged at the beginning, so you want to go slower, and then as it's starting to move, generally you're taking off about 80% engagement. That feed rate can be increased, and that's what these parameter boxes allow you to do. Okay, so we're going to go on to the next tab, just geometry. So we're going to machine the entire face. Our stock is auto-calculating from the information that we already put in, so there's nothing to select. So you can leave this box at default. We're going to go on to heights. Now I'm going to we're going to briefly review what each one of these planes means. The majority of the settings we're going to leave at default, but being the first time through, it's important to know what all this means. Okay, so we'll start at the top. The clearance height is this orange plane here, and so we have it by default set as 0.4 higher than the retract height. The retract height is here, this green plane here. So if we adjust this retract height, it's going to automatically change the clearance height. The number that's displayed here is actually the distance between the plane itself and our model's top, okay, top of the actual model. So what we're telling the software is that we want it to output rapid movements above this plane. It's above everything, clamps, anything holding it down. It won't run anything, and the machine will move at its extreme most fastest motion when it in height is at this plane or higher. Okay, the retract height currently is set to reference the stock height top, which, if you recall, is 0.04. It's right above, it's basically at our stock top. So it's going to read at 200,000. So what this is after the machine is doing a routine in one area of the part, and it picks up and retracts to move and not engage the work, to move to another position to engage the work, it's going to retract to that plane, which is 0.2 above the part. That way, when you're not changing tools, it keeps it closer to the part, moves faster, and especially if drilling cycles, you're moving around a lot, it keeps it close to the part. If you had something you needed to avoid, you might need to bump that number up. The feed height, similar to the retract height, generally is usually about the same. What it is when the cutter is going down in Z, when it crosses that plane, it starts at your plunge feed rate. Okay, and then the top height is set as top of stock right now, and bottom height, we're machining from the stock top down to the model top, which should take 40 thousandths roughly off the top of the material. Okay, so the next time I go through this tab, it won't be in that level of detail, but I'll refer to this video if you want to go back and watch that section when we program the other parts. Okay, we're going to move on to passes. So because we're planning to take 0.04 off, and the cutter we've selected is the shell mill is very big in relationship to the part, it's 3 inches in diameter, it's rated to take 0.06 off in depth. We're just going to take one pass and machine this in one pass. So we're going to leave our tolerance at default at 0.4 of a 100,000th. Our pass direction, we want that at 0 degrees. We're just going to go the full length of the part. In our pass extension, we do want to change. We want that to be a little more than the diameter of the cutter. That way that our cutter passes go off of the work and beyond the stock. These types of cutters do not cut well if they are touching material as they're moving up and down in Z-axis. Okay, we're going to leave our stock offset at default, and we're going to leave the step over at default. This is a 3-inch diameter cutter. The step over is the sideways step over, as you can see in the graphic that's displayed. And we're going to go both ways, although with one pass it doesn't really matter. And we're going to leave from other side and chip thinning alone. In this case, we don't need multiple depths. We're going to go on one pass. And we're not leaving stock behind for another cutter to remove, so we'll leave those deselected. and move on to the linking tab, which is the next one. High feed rate mode, we generally leave this preserve rapid movements box at default, and then we're going to allow rapid retract. So that means when it's lifting, it is going to go in rapid mode. And keep tool down has to do with if you have multiple zones where pockets or something deep, it gives it a maximum Z travel that it'll stay down and not pick up. In the context of this part, it's not going to make a difference. So leave that at default. Extend before retract, that is if you want it to move off of the part before it retracts in X and Y. We've already taken care of that with a different parameter. And then lead in entry. Yes, we want to lead in. Vertical lead in radius, so that would be having a vertical radius that the path would travel to meet the part, and we don't need a vertical radius with this type of cutter. In fact, it doesn't perform very well with that, and we will be leading in off of the material anyway. We do want to lead out on exit, and it's going to be the same length as the lead in. Okay, our transitions type will remain at default, which is smooth. Alright, we're going to hit OK, and we're going to see what this does. And so our face mill comes over here. Its first motion, this arrow is pointing down. The yellow is rapid, so it's going to go as fast as it can to the rapid plane. And then it's going to feed in at 25 inches a minute. And then it's going to feed in horizontally by 1.6, which is our lead in, and then it's going to do its pass at the same feed rate, feed back off of the part, and then rapid back to the tool change position for our next tool. You have just written your first line of CNC code. Alright, so we have completed the first routine in this setup, which is going to be comprised of 2 routines. Now we want to machine around the perimeter of the part to define the length, the width, and machine these small radiuses that are modeled in the corner. For that operation, we're going to switch tools and we're going to switch routines. We're going to use a 2D contour to contour the perimeter. And to do such, we are going to change tools from the Titan library to tool number 2, which is a 1/2 inch diameter flat end mill, 3 flute. Okay, so this is an example of that 3 flute 1/2 inch carbide end mill. And end mills are designed to cut on their end face and their side flutes. So the flutes are the spiral shaped features that are going down the side of the end mill, and they are sharpened to do cutting. And if it has 3 flutes, then it means it has 3 separate spirals. 4 flute would have 4, 2 flutes would have 2, and the tips are on the end. This is called a flat end mill, so it cuts flat bottom with a sharp corner, and the smooth portion is the shank, which is held by your tool holder. So this particular cutter is designed to cut to a maximum depth of where the flute meets the shank. These cutters are your primary tool on a vertical milling machine. They can be used to cut pockets, holes, profiles, very versatile, different diameters for different size features. Okay, we'll move on. And once we've selected that, we're going to select OK. Alright, so a bunch of parameters changed here. we're going to leave the default spindle speed at 4,000. We're going to leave surface speed at default, ramp spindle speed at 4,000 as well. We're going to change our cutting feet rate again to 25 inches a minute. Our lead in is going to be 25 inches a minute, and so is our lead out. Our ramp feed rate, however, is going to be about half of that. So 13 is good, and 13 is good on the plunge rate. Again, for these two boxes, the end mill is most likely engaging on 100% diameter of the cutter, so you want to move a little slower. You can break the very sharp teeth or flutes on the end mill. Now we're going to move on to the Geometry tab. Now on the Geometry tab, we have to select a contour. And by default, it's going to contour a chain, or follow a chain. And we want to machine down to the bottom of the part. Okay, and you want to check this arrow and make sure it's on the correct side of the path, the blue perimeter. If the arrow was here inside, you'd be machining on the inside of your part, and it's going to come out a lot smaller by the diameter of the cutter. Okay, so the rest of these tabs we're going to leave at default. We don't have any, our stock is already defined, it's not an unusual shape. We're not leaving tabs, which are pieces of material that connect our part to this surrounding stock. We don't need rest machining because we're not going to be coming back with another cutter to cut pockets out. Wrap tool path has to do with wrapping it around a shape. And tool orientation only comes into play in 4th and 5th axis programming, where the orientation of your spindle may not be perpendicular to the XY plane. So we're going to leave all of those at default, and then next time I go through this, I will only explain these check boxes if we have a reason to change them. Okay, moving on to the Heights tab. Now, we've machined off the top of the part. So our part is now at what is called model height. So we're going to leave the clearance height at 0.4 from the retract height. But we're going to base our retract height now off the model top instead of the stock. It's giving this red numbers, but that should go away when we change some other settings here. Our feed height is still going to be based off the top height, but again, the top of our part is now the height of the model, not the stock. So we're going to change that to model top. And what do you know, our little error goes away because these two values are now the same. Generally, your retract height needs to be the same or greater than your feed height. Okay. And our bottom height is going to be based off the contour we selected. So the software is going to calculate that it needs to travel that down to that distance. Now we're going to actually travel a little bit past the bottom of the model. We have extra stock there, and that way if our thickness comes out on the high of the tolerance, we're sure to not have a little burr left on the other side. So we're going to go 0.01. Our thickness tolerance is 0.005 or 5/1000ths of an inch. So if we leave 10/1000ths, we'll definitely fully clean up when we machine off the other face. If we don't, we know our part is too thick and out of spec, and will need to be reworked. Now we're going to move on to the next tab, passes. Now in Titan's original videos, he takes this off all in one pass, and in my opinion he's trying to show off what Kennametal tooling can do, but you're not going to get optimum life out of those cutters by kind of abusing them that way. We're going to take this in more than one step. It's also safer, and not necessarily, if you're running the right feeds and speeds, not necessarily faster the way he does it. This could be most likely more accurate as well. So if you've looked at any of the old Titan videos, he's going to show you slightly different setup here. We're going to leave tolerance at default. We want to climb mill whenever possible. That means the rotation of the cutter is going in the same direction of movement, as opposed to conventional milling, which the cutter goes against the direction of motion. On a modern CNC machine, they're very tight tolerance in their movement, and you can climb cut, which produces a better finish with most cutters in most materials. There are some exceptions, and generally you only climb mill with a CNC machine. If you were using a manual machine, you have to conventional mill almost all the time, or you can have the screw backlash and damage the machine. Okay, this compensation type. It says in computer by default, and we're going to switch it to where. And the reason we're doing that is if you have it on the default, the CNC program will not output a code that allows the operator to adjust the machine based off the wear of the cutter. So as the cutters are used, they get slightly smaller in diameter over time, and the operator can measure the parts and compensate at the machine if you select wear. It allows them to do that. Okay, we're going to skip the compensation radius and leave that alone. It will auto-calculate based off other things we enter. We're going to skip make sharp corners. We want the end mill to actually round the corner as it goes around, as opposed to forcing a sharp corner. Our minimum cutting radius is irrelevant in this geometry. What that does is says, I don't want you to go into an area with a radius smaller than that number. It's a waste of time with the cutter. We'll come back with something else. And it'll ignore that feature. We don't have any, this toolpath doesn't have any geometry like that. Multiple finishing passes, we're going to leave unchecked. And we're going to make sure that our finishing feed rate is at the same feed rate as our other passes. We could have it go slower, but in this case we're going to leave it alone. And we're going to skip repeating finish pass. That would be for spring pass. If you have a cutter that's under heavy load, when it does its first finish cast, it may flex, a real flimsy tool. So a repeat finish pass would move it with the same exact numbers, just go back and do it another time, and that cutter, being under less load, may shave off just a little bit of material based off how it was deflecting the first time it came through. We don't need that. We're going to skip the finishing overlap. And lead end distance, we're not going to worry about that. That parameter has the cutter stop before the end of a part. So if there was something that you needed to avoid, it's possibly you could say I want it to stop an inch from the end of the cut, and it will. Roll around corners, we want that parameter on. Tangential fragment extension, we're going to leave that alone. We're going to leave preserve order alone, and both ways we don't want to go climb and conventionally cut, so we're going to leave that deselected. We do want to do roughing passes. So what we want to do is do a roughing passes that go around the part, leaving material for a finish cut. And we also, so that's what this parameter is for. Our maximum step over, generally you want it to be 80% of the cutter diameter. If we were to take our handy dandy calculator, or you can calculate in head if you feel inclined, we're using a 0.5 diameter cutter, and we're going to multiply that by 0.8, which is the factor associated with 80%, which gives us a resultant of 0.4. So our maximum step over is going to be 0.4. Smoothing deviation, this is for the roughing cut. It doesn't have to be as fine as our finish cut. It's fine at 0.004. We're going to do a maximum of one side step over. So we're just going to do one roughing cut. Okay. Now, because we selected this box, you may have not noticed it, but this step over box suddenly appeared. And that's how much we're going to have it step over for a finish cut. So we're going to set this at 0.1. So after it's done its roughing cut, it's going to come back and do its finish cut at 0.1. I'm sorry, we wanted that at 0.01. So that's 10,000ths of an inch. And by changing that number, we have our radius compensation change. Okay. Now, moving on. This is a long tab, so bear with me. And I think in the notes it's spread out over more than one page because it couldn't fit on the height of a 8.5 by 11. So we're done with roughing passes. We do want to do multiple depths, and again, Titan did it all in one shot, but you know, you can break a lot of cutters that way, and especially when you're new at this. So once we select the multiple depths, this menu gets longer. So it's asking what's our maximum rough step down. Our maximum roughing step down is going to be 0.25. Okay. And then our finishing step down is going to be set at 0. And our finishing step down distance, we're going to set at 0.01. Okay, scrolling down, we are going to be approaching along the wall, and we're going to finish only at final depth. So what's going to happen is we're going to get multiple steps, 3 passes, taking off the distance for the roughing, but our finish cut is going to be at full depth. So it's going to use the whole height of the flutes of the end mill to give us a nice clean finish. And we're going to select even step downs so that they're evenly distributed. And we're going to skip order by depth because we're not doing multiple pockets. We're going to deselect order by islands. It doesn't really matter. There's aren't islands in this. And we're going to leave the rest by default. And we're going to skip down to skip stock to leave and go down to smoothing. Now the smoothing box, which I guess rolls you off the screen here, we're just going to leave that at default at 4/10. So that smoothing is for the finish cut. Will only really come into play with the corners with this geometry, but its movements are going to average out so you don't get facets on your part. Okay. All right, going to the next tab, linking. Linking, we're going to leave preserve rapid movement at default. We're going to leave the rapid retract at default. We're going to leave safe distance alone at default. Keep tool down we'll just leave that at default. It's not coming into play with this routine. Lift height is 0 is fine. Leads and transitions, yes, we want them. Our horizontal lead in is going to be 5/10 or 5/50,000ths. That is a radius. I'll try to display it here. It's a radius where the end mill will follow this green radius path, and it decreases the incidence of a mark left by where the tool starts engaging the part and finishes engaging the part. It's called a dwell mark when you see a mark from that. Our sweep in angle will be 90 degrees is fine. A linear lead-in distance, which we need some for the programming code, is the straight section of this lead-in as it's going into the material. And that references the lead-in feed rate. We're going to leave perpendicular alone. Vertical lead-in radius, in my opinion, we don't really need it, so we're going to put in 0 there. And so vertical lead-in radius is, as you see in the graphic, the cutter comes in and leads in as an arc into the material. Some of the older machines can't really actually handle that movement, but if you were, say, plunging into a pocket, that might have some good results for you. But with a profile going around the outside, I don't see the advantage of it. We do want to lead out as it exits, and we want that distance to be the same as the lead in. For the purpose of this part, we're going to ignore ramp. We're not plunging into material, we're coming in off the part. Okay. And positions, pre-drill positions and entry positions, we don't have a real specific need to enter the work in a specific spot. You could use this entry positions to say I want to start here in the front, so you as operator can see the end mill coming down. So why don't we do that? We'll select entry positions and okay. All right, and we're going to hit OK and see what this does. So we have 1, 2, 3, 4 roughing cuts, and then at the bottom around the inside is the finish cut. Just moves in 10 thousandths, goes around again. Each of those lead-ins, we have the cutter rapiding down to the rapid plane, and then it's going to feed into the work, and it's going to come down to the first level, arc into our material, arc out, or go all the way around, arc back out. Then it's going to feed down to the next plane, go all the way around again, 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 and then come back in and go one more loop around the track, taking off a finished pass off the entire face. Okay. So you have just finished your first setup, which will be your first CNC program. Now let's go to the next step and simulate it so you can see what you've done. So you highlight the setup, or you can highlight an individual operation and simulate it. We want to show the entire program with all the routines in order. You highlight the setup and you go up to this icon here that says simulate. Press that button and a box shows up and a solid modeled version of the cutter and the path all display. We want to select this box that says stock, and what that does is it displays the stock. The gray was displaying your finished part size. Okay, once you've done that, you're going to come down and press this Start Simulation arrow, and you're going to see the cutter come across, mill the face, our 1/2 inch end mill comes in, machines the perimeter to size with a plus 10 thousandths for a rough cut, comes and makes another step, another step, and now it's doing a finish cut, just skimming off 10 thousandths. And that end mill should have taken it to finish size. And that completes the first operations on the machine. The next step will be to flip this part and machine off this roughly 1/4 inch extra material, 210 thousandths or 20 thousandths or whatever it ends up being. Now while we're here on the Simulate tab, I'm going to go over a few other things. You can change some options on how it renders. Some people don't like seeing the holder. You can go to the info and it gives you a bunch of information like your highest spindle speed with 4,000 RPM, the maximum positions were here, the different, the last operation information that was on that. It didn't detect any collisions where the way the tool's modeled, the holder didn't hit the part. Your starting and finishing volume of material. And then this third tab here is good because it tells you multiple operations, number of tool changes, the distance, but also an estimated machining time of 3 minutes. Now that might be a little long for this part. We were a little conservative with our feed rates and with the step overs. We probably could have gone a little more aggressive on that. So you can imagine if we were running full tilt on here, this routine here this program should probably run about 1 minute, 1.5 minutes long. And took you a little longer than at the program, but it's much more efficient than programming by manually. Okay, so if we're done with all that information, we're going to hit close. Oh, and one footnote about the time: this is an estimate, depends on the equipment, depends on the size of the machine, tool change cycle times may affect this number. So often it's a little bit low than reality. So you only want to use this for estimation purposes. But if you see something like 2 hours here, then that's probably something you're going to want to change, because it's going to be hard to make money if you're taking a super long time like this. Okay. All right, let's hit close, and we pop back to this window. Okay, so we have one more operation to do on this, and it's to bring it to thickness, like I mentioned. So that's going to be a separate setup. The part is going to have to be removed from the machine, flipped over, and you machine off the opposite face. So for that discrete setup, you need to create a new setup. Okay, so our new setup, similar to last time, is you're going to set up the stock first. Our offset's going to stay at 0.04 because in the zone we're cutting, there's still material on this distance down here below. So we're going to be flipping the part and clamping on the finished sides of the part. So our origin is going to move to a different place. So let's go to the setup. We're going to use model box point. So it's going to change from our reference being on the stock to the machined profile, which is very accurate. Okay, so to set our orientation, again, we're going to use select Z axis plane and X. So this is our Z-axis plane. So our axis gnome, the Z, should be pointing at our spindle. And right and left, X should be positive to our right. So we're going to select this edge for the X-axis, and we're going to flip it. This puts our X-axis and our Y-axis positive in the correct orientation to our part. Okay, so we are now going to set our origin, which is going to be, again, off a model box point. So it's this corner here, which will represent the corner by our vice stop and our vice fixed jaw. Okay, so if we look down in plan view for our second operation, our origin is at the theoretical intersection of that corner, not on the stock. You never want to base an operation off stock for anything but the very first operation. The stock is raw cut. It's going to be off by how much you offset when you first set up. Every following operation should be based off a machined face that you can indicate to. Okay, and we'll work with you in the shop on proceeding with that. We're going to go to our third tab, which is post-process, and we're going to call this program 1002, and we're going to call this operation 2, and again we're going to use work coordinate system 1. Okay. We're going to select OK. On the left you should have setup 2 appear, and any new toolpath we do go into that setup. This last program setup is only going to consist of a face mill operation, so it's going to be very similar to the one we did here, except we're going to take off this thickness in multiple passes. So we're going to start with 2D face, and first we need to select from the Titan library tool number 1, which is our face mill. We're going to set this at 4,000 RPM and 25 inches a minute, all the way down the line. If you want a more in-depth description of this, roll back to the operation facing 1 that we did. Okay, we're going to move on to geometry. There's nothing to select. Our stock parameters give us the size of the geometry we're cutting. Tool orientation only comes in play in 4th and 5th axis. We're moving on to our clearance heights. So now we've flipped our part, and we are basing heights off stock now. So our retract height, our clearance height is going to stay at default at 0.4 above our retract height. Our retract height is based off our stock top and adding 0.2 up. Our feed height is going to be based off our top height, and it's going to be 0.2 higher, and it is also based off our stock top. Okay. Now our bottom height is our model top, so our cutter is going to be machining off the material between the top height and the bottom height. Okay, and that is the difference between the light blue and the dark blue plane. Now we're going to move on to the next tab, which is passes. Tolerances, we're going to leave at default. Pass direction, 0 degrees fine. Pass extension, we want to set at 1.6. Our stock offset is 0. Our step over is going to stay at default. Our cutter is bigger in diameter than the width of the material, so we're just going to leave it that way. We do want to go in both directions, and we're going to leave these two at default, but we do want to do multiple depths this time, which we did not do last time. Our maximum step down is going to be 0.04, and we're going to go from both sides, and we're going to do a finishing step, which opens some other boxes. Our feed rate is going to be 25 inches a minute, but our finishing step down is going to be 0.01, so we're going to get a nicer finish on that last pass. And we are going to use even step downs. Now when we select this, we should get multiple passes going back and forth, milling this down to thickness. So we'll select, oh, we're not ready to select OK. We're going to go to linking. We're going to leave our preserve rapid movements alone. We're going to allow our retract, keep tool down. Basically everything here is going to be at default except for no vertical lead in radius. We're going to leave that at 0. We do want to lead in and out, and we do want transitions to be smooth. So we'll set OK, and it takes a little bit of time to process. As you see, we get multiple steps down and a finished pass at the bottom. Okay, so if we were to simulate this, you would pick on simulate. Make sure that the stock is selected and hit go. And it's going to come down and whittle that away 40 thousandths at a time. Until we see the part perimeter. Okay? Alright, we're going to select close. Now, you want to make sure you're saving more often than I had. Save early, save often. And because you're cloud-based, you lose internet connection. You don't want to lose your work. Okay, now I'm going to show you a couple other steps. And these steps are done after you're done programming. The first one is a setup sheet, and the setup sheet is what you're going to do and submit on Canvas to indicate to your instructor that you've finished your programming. Your instructor will review that. He or she may also review your CAM file before giving you approval to run. You are not to run any programs in the lab until you've been given approval from the instructor. We're going to create the setup sheet first, and if you have two setups, you need to submit a setup for each one of them to have a complete programming submission. Once you have that selected, you select this icon that looks like a form, and you're going to need to say a location that you're going to save it to. I'm just going to hit select folder for this example. And what will happen is in your web browser, a setup sheet like this will appear. It's helpful if the view you've selected actually displays the origin in a way that is how the operator can see it and knows how to set up. So in this case, I probably could have zoomed in a little more so that you could see where the origin is. It gives you a whole bunch of information like the stock size, your part finish dimensions, and the upper extents and lower extents of the coordinate system. It also gives you the number of operations, number of tools, what tools are used, what tool numbers, the maximum height of cutting and minimum, and that's something that your instructor will screen to make sure that you have a program that may be cutting too deep and into the fixture, which is not good. We're also going to be looking at your maximum feed rate and your RPMs to make sure they're in line with our standards for the lab for safety. It's a good way to self-screen too if you made a mistake. If you accidentally punched in 250 here, it'll show up there. Okay. Then you have a tool list, which is a list of every tool you're using. Then there's a list of operations that those tools do with their own minimum, maximum, and RPM rates. Once you have approval from your instructor, you will want to make a hard copy of this and bring it to the lab. It will, one, help you with setup. It'll help you with asking for the correct tools from the tool attendant. And you will need to submit it in your final paperwork package with your part, as if you are programming for a company, and that documentation then becomes part of the setup information for the machinist that's going to run the part. So to get full credit in your lab assignment, you need the hard copy. You can save this as HTML or PDF and upload it on Canvas. Okay, so you'll do it for your first setup, then you'll come back and select your second setup, do the same thing. And that one will display operation 2 and setup 2, and it's only using one cutter. You'll upload that as well. Then, when you get approval to actually generate the program to be on the machine, you will then highlight the setup similarly and hit this post-process button. Now the post-process is like a compiler and other types of programming, and you're going to search on that list for the brand machine that you're going to run your program on. So you can use this software to program something and run it on multiple machines, provided you select the correct post-processor, which outputs the blend of programming code appropriate to that brand of machine and configuration of machine. You'll want to change your output folder, maybe do a USB drive, because that's how you'll load it on the computer or on the controller. And then your default program number and program comment should come through from the first tab you set. And once you have all that done, provided you have HAAS, pre, and GC post-processor, you just select this post button, and it'll ask a location to save that program. it's done post-processing, it'll pop up with HTML version of the code. And this you can quickly screen, but you can see here's your routines. It's phase 1, that's what you labeled it. This was operation 1 with program 1001. It's using tool 1 and tool 2. And the first operation's facing, and this is the code associated with that. And then the contour cut, 2D contour, is being done with tool number 2, is all here for the rest of the page. This is a relatively short program. And your work coordinate system will be displayed as, G54 is the one that we selected. Okay. All right. So, closing that and concludes the first tutorial, which includes your first 2 programs to produce the TITAN-1-1M configuration of the part.